Hello and welcome to week 11 in Statistics for Psychology, and an exciting time. We're now moving into the area in this class where we're going to be discussing terms like significance and our first steps toward understanding the relationship between variables beyond correlation, and actually looking to see if the data that we've collected in our experiment, in our observations, in our study of existing data, whatever our research method is, to determine whether or not our data is significantly different from what we would expect. So we reintroduce at this point in Chapter 9 the normal distribution. That's that curve like this. I have some graphics here in just a little bit. I'll be showing you that. The normal distribution and something called z-scores. So let's take a look at a normal distribution. What this curve represents is the frequency distribution of sample means, as we have already discussed. So what we have, this example, what it exhibits is IQ scores. Those IQ scores are right along here. So an average of 100, we have 130, 85. You know, these are IQ scores or mean IQ scores. And up on this axis, we would have the number of times we saw that mean going like this. So if we were going to look at the incidence of 70 occurring on an IQ test, we go there and go here, and that's the number of times. Same with the average here, 100. This is the number of times you would see that mean. Now, the way we look at this particular distribution, taking out all this stuff here, takes a while. When we're looking at a distribution like this, we express it. A normal distribution is expressed as vertical lines represent units of standard deviation. Now, in IQ, the mean of all IQ tests is 100, with the standard deviation of 15. It's statistically made to be that way. So here we have the average of 100, and one standard deviation this way is 15 points. Another standard deviation this way is another 15 points. And the same, of course, on this side. Now, that 15 additional points from any given point here is considered 1 unit of standard deviation. So what we're essentially looking at when we look at z-scores, z-scores is an expression of the measurement, in this case intelligent, in units of standard deviation. And remember, units like miles or centimeters or degrees centigrade, degrees Fahrenheit, those are units of measure. So in this particular example, we have one unit of measure, which is the scores. 100 is the average, and then the scores along the number line. But then we can convert those into units of standard deviation. Now I'm going to use some easy examples for that. We have here the number 15 right here. And that as you know, is 15 units above the average of 100. So we could convert the 115, and instead of saying a score of 115, we can say they scored 1 standard deviation above the mean. With the 85, we get the same thing. We have 1 standard deviation below the mean right there. So minus 1 standard deviation. And of course, there's all kinds of units in between. So about halfway here, maybe 7.5 points, is going to be 1/2 standard deviations. The actual score might be 107.5, but that would translate into 0.5 standard deviations. This right here is called a z-score. These right here are considered the same data, except it's expressed in units of standard deviation. So we can speak to any statistic that we have, and we can give it the raw score, which may not have a whole lot of meaning, but then we can look at standard deviations, and we can get a more deeper meaning as to where that particular score rests in relation to all the other scores in that distribution. And in the course book, there's some examples, like how do we compare weight, let's say, when the distribution, the mean and the standard deviation of two different animals is different. How can I compare how much overweight I am compared to how much overweight a chipmunk is? You can't just look at the units. You just can't look at pounds. That would be ridiculous. You'd have to look at how many standard deviations am I above, how many standard deviations is Chucky above, and then you can figure out which one of us is in better shape in relation to our peer people or peer squirrels. Did I say squirrels? Okay. A little bit of my OCD coming out there, or my ADHD, I should say. So that's kind of what we're talking about this week in this chapter 9, is looking at converting regular scores into z-scores so we can compare different types of measurements. It's like finding a common unit of measurement would be the mathematical thing for that. In the discussion, what I'm having you do is simply take a look into the literature that exists out there within the field of psychology and find examples where z-scores are used. Usually we will see those, and often we'll see them reported out when people are using standardized tests. And the whole field of standardized tests, whether you're talking about the SAT or an accepted measure for depression, standardization means we have the figures for that standard bell-shaped curve across populations. Let's say in the big IQ test, they've measured those across all sorts of different populations, sometimes all over the world, and they've got all of that data so that when we use that test for comparison, we can compare how we've done compared to everybody else that's taken that test. And it's a very easy tool to use because I can just take my score and view it in terms of how many standard deviations above or below the mean I am in relation to everybody else that's taken that test. And another factor that comes into play here is in IQ specifically, if we're going to look at this as an IQ test, okay, which was what these scores are, you'll see these numbers right here, 130 and 70. These are the points at which we have +2 standard deviations or -2 standard deviations. And in the world of abnormality, 2 standard deviations above or below the mean is sort of where we draw the line in the sand as to something being abnormal. This is all abnormally high, and this is all abnormally low. Now, the significance of 70 and 130 is those are the scores in a standard IQ test that are used to determine developmentally delayed, 70 or below, and gifted and talented or genius, depending on how you're actually, what your goal is in using the IQ test, 130 and above. So those are extreme measures. But what I'm trying to get to you, if you have something that scores 2 standard deviations above or 2 standard deviations below, that's a pretty significant chunk. That's a pretty significantly different score than most other people. You can see on this graphic again, you can see that everything above 2 standard deviations is only 2.2% of the population. Everything that's below is only 2.2% of the population, roughly 5% up on either side. Okay? That 5% will come up again. So stay tuned for that. When we start talking about significance, we start talking about, is it in that 5% rare range when we look at something in order for something to be significant. So the discussion has you look at examples of this. Usually you're going to find them in the literature when standardized tests are being used in that particular study. And discuss that. Discuss your findings in the discussion board. The quiz for Chapter 9 looks at the application of z-scores, exactly what I was talking about, the comparison of different distributions to see where we're at, to comparatively in terms of animals or whatever. We can also compare other measures. As long as we can convert things to standard deviation units, we can look at 2 different measures in a similar way. Then we go into Chapter 10 because we don't always have access to standardized population scores. So what do? We have another test called a t-test, and there's going to be a number of t-tests that we're going to cover in this class. And t-tests reveal to us the same sort of z-score-ish thing, but it makes presumptions about our sample related to the population from which we have drawn that. If we don't have all the data, we don't have standardized data, it uses the sample data to estimate what the population data would look like, and then we can do that comparison. It sounds a little iffy, you're looking at my sample and what if my sample's really odd? But the statistical methodology that goes into that takes into account what the population may look like. In fact, your sample, every time we sample something, it's an estimate of the population. The mean is an estimate of the population. The standard deviation is an estimate of the population standard deviation. So if you take a sample, that's particularly if it's a good sample. We'll see, for example, I talk about in the book that the larger the sample, the more it's going to closely represent the population, right up until population -1, right? And then get everybody. So population -1, if I had a sample that included everybody except one person, it's almost going to be, realistically, it's going to be identical to the population data. So the bigger the sample, the more it represents the population from whence it came. So we have to know, when do we use a z-test to get z-scores to make decisions about the relationships between our variables, and that's pretty much when we have a mean and standard deviation for the population, the kind of data you get from a standardized test. When we don't have the mean or standard deviation of the population, we might only have the mean, or we might not have either one of them. We have to use t-tests in order to make those decisions. And there's some limits to that. We have to have some data related to the population. We're going to get into t-tests later where we're comparing 2 groups. And you'll see that we don't even really need the standardized part, because we're just seeing if groups are significantly different from each other. That kind of thing. We won't need to bother with any population type estimates or real data as we would get when we're using z-test and standardized testing. But nonetheless, there we go. We have Chapter 9, normal distributions, and the introduction of converting raw scores to z-score units, or units of standard deviation. We have the discussion to find z-scores in the literature. We have the quiz on the applications of z-scores. Then we move into Chapter 10, when do we do a z-test, when do we do a t-test. And then the Chapter 10 assignment, we look, it gives you an example of subliminal perception. And here it's interesting. You have to understand the reason in this particular example we didn't need to have standardized scores, or we can guesstimate. We can guess what the average is going to be, what the expected average is to be, because the average is going to be by chance. It's going to be a 50% chance. If something's going to appear or not, it's yes or no. So when the questions are yes and no, then pure chance of guessing that particular the right answer is a 50-50 chance. So the norm, the expected norm mean of that would be 50%. And then we look at our population, we look at our sample, and we see, is there anybody in there that got more than 50%? Like flipping a coin. We would expect that if I was going to try and predict how many times it's going to show up on heads, okay? If there's no weighted coin, if there's nothing like that, then the chance of it being heads is 50%. If I guess it to be heads more often than 50%, something's happening. I have ESP. I have a vision of the future. I can tell when the coin's going to, or something's wrong with the coin. Those kind of things. So this is an important transition when we're looking at moving from descriptive statistics into much more predictive and even into decision making and hypothesis testing. We're into our first tests where we're looking at z-scores if we have standardized tests, and if we have standardized data, and then the first introduction to t-tests where we use the data from our sample to estimate the population data, and we make our decisions as to whether something's unique or not based on that. I don't know if this helped or harmed. This is what I'm going to give you for right now. This is usually kind of a really lengthy discussion when I'm in a face-to-face class, but we'll go with this. Hopefully everything is all right. So please email me any questions that you might have, post them in the discussion boards, and have a great week. This is a very, very important transition. We're going to be then quickly making our way through quite a number of t-tests, and you'll see how those relate to different designs. We'll get into control groups. We'll look into comparing different groups, different populations, that kind of thing when we get into the more advanced t-tests. So have a great week, and like I said, reach out if there's any questions.